In this class, we'll discuss how base kits evolve in the Schrodinger picture and the Heisenberg picture, right? And based on that discussion, we'll talk a little bit about transition amplitudes. We have seen that states evolve in the Schrodinger picture and operators remain unchanged, okay? Whereas in the Heisenberg picture, it's operators that change with time and states remain unchanged, right? Now we have to ask the question, what happens to base kits, right? What happens to base kits? Do base kits behave exactly like states, right? Or is it different? So there's a common misconception, right? And it's easy to have this misconception. The misconception is that as time goes on, all kits move in the Schrodinger picture, right? In fact, this is not true. We are going to see that base kits do not change in the Schrodinger picture, right? We also might have the misconception that all kits are stationary, unchanged in the Heisenberg picture. This is also not true. We will see that in the Heisenberg picture, base kits evolve with time. All right. Now, the important point is to distinguish the behavior of state kits from that of base kits. All right. So we have to be careful here. We have to distinguish the behavior of state kits from that of base kits. We started our discussion of Ket spaces by remarking that eigenkets of observables are to be used as base kits. Right? So in quantum mechanics, the base kits that we are interested in are formed by the eigenkets of Hermitian operators or eigenkets of observables. Okay, we have already seen this. So bases in quantum mechanics, the bases that we use in quantum mechanics are actually eigenkets of observables. Okay. Now we can ask, what happens to a defining eigenvalue equation? Now these eigenkets are defined by the eigenvalue equation, right? So eigenkets of an observable is defined by the eigenvalue equation, right? Eigenvalue equation of this form, A acting on ket A prime is equal to A prime multiplied by ket A prime. Okay. Now we ask, what happens to this eigenvalue equation, right? What happens to the eigenvalue equation with time? Now let's start by looking at the Schrodinger picture. In Schrodinger picture, A does not change, right? The operator does not change. So the base kits obtained as the solutions to this eigenvalue equation at t equal to 0 must remain unchanged. Right? So what are base kits or what are these eigenkits? These eigenkits are solution to this equation. Right? Now if A does not change with time, that means that the solutions remain the same. The solutions to this equation remain the same. Okay. So if you obtain the solution to this equation at time t equal to 0, right? Since this A does not evolve with time, it's always the same operator, right? The solution will remain the same at any later time, okay? So the solution must remain unchanged because A does not change, right? Because the defining equation does not change, so solution also have to remain the same. Now, unlike state kits, the base kits do not change in the Schrodinger picture. Okay, so this is something important that we have to remember. State kits evolve in Schrodinger picture, but base kits, all right, we have to use the same base kits. Base kits do not change in the Schrodinger picture. Okay, because we are defining the base kits. We are taking the base kits which are formed by the eigenkets of an observable. Okay. So in the Schrodinger picture, generally state kits change with time, but the base kits remain the same. They don't change. All right. What about the Heisenberg picture? All right. We know that in the Heisenberg picture, operators evolve. Operators are time dependent. Okay. So we can write A h of t is equal to u dagger A of 0 u. Right. This is how operators evolve in the Heisenberg picture. Right. Now A of 0 is the same as the Schrodinger picture operator because the Schrodinger picture operator at any time is A of 0, right? Because it does not evolve with time. So at time t equal to 0, both pictures coincide. The Heisenberg picture and the Schrodinger picture coincide. So we can have the eigenvalue equation at time 0 and this would be the same in both Heisenberg picture and the Schrodinger picture. Alright, suppose this is the eigenvalue equation at time t equal to 0. This would be the same in both Heisenberg and Schrodinger pictures. Alright, now let's apply a u dagger to the left. Right, so just to understand this, so u dagger A of 0 ket A prime is equal to A prime u dagger ket A prime. Alright, we see that if we have u dagger A of 0 u, alright, if we have u dagger A of 0 u, we'll have AH. So let's introduce a u dagger u in here. So this equation will become u dagger a of 0 u dagger, because u dagger is I, acting on ket a prime is equal to a prime multiplied by u dagger ket a prime. Okay, so what is u dagger a of 0 u? This is ah. This is uh, the operator in the Heisenberg picture. So this is ah of t, right? This is ah of t, and then we get an equation. We get a different eigenvalue equation. Ah of t u dagger ket a prime is equal to a prime u dagger ket a prime. All right. We see that the eigenvalue equation has changed because the operator has changed. It's not the same operator. Here we have a of 0. Here we have a different operator. Right? This was not the case in the Schrodinger picture. In the Schrodinger picture, the operator did not change, and so the eigenvalue equation also remained the same. But over here, the operator has evolved with time, which means that the eigenvalue equation that we need to solve has changed. And here we have got the eigenvalue equation for AH at time t, or this is the eigenvalue equation for the Heisenberg operator, for the Heisenberg picture operator at time t. Okay. Now, if we hold on to the view that eigenkets of observables form the base kets, all right? Suppose we want to keep this idea that eigenkets of observable form the base kets, all right? But we see that the eigenkets have changed because the operator has changed from a of 0 to a of t, right? Or ah of 0 to ah of t. That means that the eigenkets also have changed, all right? This means that we have to use u dagger ket a prime because these are the eigenkets of the operator, of the Heisenberg picture operator, right? So this set must be used as the base kets in the Heisenberg picture, all right? So what does this mean? This means that as time goes on, the Heisenberg picture base gets denoted by ket a prime t with a subscript h. All right, this changes, and the change is like this. If you want the base ket at time t, you take the base ket at time t equal to 0 and then apply a u dagger to it. All right, because these are the base kets now. So the Heisenberg picture base kets evolve according to this equation, right? Ket a prime comma t in the Heisenberg picture is given by u dagger acting on ket a prime. Right? Now you see that this evolution is opposite when compared to the evolution of states in Schrodinger picture. If I take the evolution of states in Schrodinger picture, this is given as u acting on ket alpha, right? The state at time t is given by u acting on the state at initial time, right? You see that the sense of evolution is opposite here, all right? So we can say that the Heisenberg picture base kets evolve oppositely when compared with the Schrodinger picture state kets, all right? Now we can also say that the Heisenberg picture base ket also satisfies an equation, a time evolution equation, right? We can call it the wrong sign Schrodinger equation. Okay, what's the correct Schrodinger equation that governs the evolution of state kets? We know that the correct Schrodinger equation is IH bar partial derivative with respect to time of alpha comma t is equal to H operator, Hamiltonian operator acting on ket alpha comma t. This is the correct sign Schrodinger equation. This is how state kets in the Schrodinger picture evolve. All right. Now we are asking if this relation is true, what's the equation satisfied by the Heisenberg picture base kets? Right, so let's look at that. We know that, so we just said that ket a prime t is equal to u dagger ket a prime. All right. Now u dagger is simply e raised to I h t by h bar acting on ket a prime. Right? Because u was e raised to minus iht by h bar, so u dagger is e raised to iht by h bar. Okay. Now let's take IH bar partial derivative with respect to time of ket a prime comma t. Right. So we take the derivative on this side also. This becomes I. So there's an IH bar here. So let me put that IH bar. When I take the time derivative of this thing, all right, what I get is IH by h bar and then e raised to iht by h bar ket a prime. Right? So this I and I will multiply to give a minus sign. H bar cancels. Okay. So this is equal to minus h. Right? So this is minus h, and what we have is e raised to iht e raised to iht by h bar, or sorry, exponential iht by h bar acting on ket a prime is what we called as ket a prime comma t in the Heisenberg picture. So these are all base kets in the Heisenberg picture. All right. So we see that the equation, that the evolution equation that's obeyed by the base kets in the Heisenberg picture is ih bar partial derivative with respect to time of ket a prime comma t in the Heisenberg picture is equal to minus Hamiltonian acting on ket a prime comma t in the Heisenberg picture. Okay, that's the equation we have given here. Right. Now, the eigenvalues, right, they don't change with time. Right. So we can look back at the previous equation. The eigenvalues themselves remain as the same. Right. Both the operators and the eigenkets change, but the eigenvalues remain the same. Okay. We have proved a theorem on this to this effect. Right. We have seen that unitary equivalent observables have the same eigenvalue. Right. They have the same eigenvalue spectrum. We have proved this theorem. Okay. So we see that this AH of t is equal to, it's given by u dagger A of 0 u. Right? We see that they are connected by unitary transformation, unitary transform, which means that these are called unitary equivalent observables. A of 0 and AH of t are unitary equivalent observables. Right? And we have already seen that unitary equivalent observables have the same eigenvalue spectrum. Right? So that's the reason why we see that AH of t and A of 0, as we have seen, have the same eigenvalue. They have the same eigenvalues. Okay. Now let's expand AH of t in terms of the base kets and bras of the Heisenberg picture. Right. So we'll take the eigenkets of AH of t, right, as the basis and expand AH of t in the basis of its own eigenkets. Right? So we have already seen this result. If you want to expand an operator in the basis of its own eigenkets, we can write it as A is equal to sum over A prime. Right? We'll have ket A prime, the eigenvalue A prime, and then bra A prime. Right? Or in other words, we said that this is equal to sum over A prime, A prime lambda A prime, where lambda A prime was called the projection operator. Right? So I hope you remember this result that we obtained in the first chapter. Right? If not, you can just prove this right now. Right? You just insert an identity operator on this side in terms of its own eigenkets, put another identity operator on this side, again in terms of its own eigenkets. All right? Use the eigenvalue equation and the orthonormality relation. So you'll have a Kronecker delta, you carry out one of the summations and you'll get this result. Right? This is quite simple. So in the same way, we can write AH of t, we are expanding it in the eigenkets of the same operator, and the eigenkets are defined as ket A prime comma t with the subscript h. Right? So this is the eigenket and this is the eigenbra. Right? So this subscript h comes here. Right? This is the subscript h, means that we are talking about these eigenkets or base vectors, base kets and base bras in the Heisenberg picture. All right. Now we have already seen that ket A prime comma t in the Heisenberg picture is given by u dagger acting on ket A prime. That's initial base ket. Okay. So the corresponding bra here is given by bra A prime acted upon by the unitary operator u. Right? This is just taking the corresponding bra. Okay. The eigenvalue A prime is still written there. Okay. Now, since these are linear operators, we can pull this out and we see that this is equal to, all right, this is equal to sum over, so I think I'll pull this out, u dagger sum over A prime, ket A prime, eigenvalue A prime, bra A prime, okay, and then you also have a u. Now what is this? This is the expansion of the operator A in terms of its own eigenkets. All right, so we can write this as u dagger. All right, this is the operator, Heisenberg operator at time 0, because we are using the eigenkets at time 0. All right, and then u. But at time t equal to 0, the operators in the Schrodinger and Heisenberg picture coincide. So we can write this as u dagger a of 0 u, right? Or a of 0 can also be written as a Schrodinger u. Okay. And this is a result that we already know. We know that the Heisenberg picture operator at time t is related to the Schrodinger picture operator by this relation. Right? So we get back this relation. Here what we have done is that we get back this relation by assuming that get a prime comma t is u dagger get a prime, right? Which means that everything is consistent, right? All this is consistent. So this shows that everything is quite consistent provided the Heisenberg baskets change as in equation 5. So if they don't, so the equation 5 was this: get a prime t is equal to u dagger get a prime, right? Now, if this is not the way in which the Heisenberg baskets change, then we cannot reproduce this result, all right? We would run into contradictions, all right? So this actually shows that everything is quite consistent only if we assume that the Heisenberg baskets evolve according to this equation, okay? Now we can also see that the expansion coefficients of a state ket in terms of baskets are the same in both pictures, all right? So if you look at this, this is in the Schrodinger picture, right? Let's first talk about the Schrodinger picture, all right? So this is the state at a time t in the Schrodinger picture. There's a u acting on the state at time t0 or t0 equal to 0. That will give you the state at time t, all right? Now I can project it onto the base ket, right? I can project it onto one of the base directions, and that will give me the expansion coefficient, all right? Now when we go to Schrodinger picture, when we go to Heisenberg picture, the states don't evolve with time. The states don't evolve with time. So state ket will remain as ket alpha comma t0 equal to 0. It remains like that, right? But this base bra will change, right? We know how the base bras change because we already said that this is how the base kets change in the Heisenberg picture, right? Ket a prime comma t is equal to u dagger ket a prime. If you take the corresponding bra equation, bra a prime comma t in the Heisenberg picture would be equal to bra a prime acted upon by u, right? So instead of this bra a prime in the Schrodinger picture here, we'll have a bra a prime acted upon by u because the base bras evolve in the Heisenberg picture, whereas the state ket does not evolve in the Heisenberg picture, so it remains as the same. But if we look at the expansion coefficient in both cases, we see that both these expressions are exactly the same. All right, both these are bra a prime u ket alpha comma t0 equal to 0. Here also it is bra a prime u ket alpha comma t0 equal to 0. All right. So this is like if when we can talk about a rotation in a coordinate system, we could actually rotate a vector, for example. Well, let's talk about a vector like this. We could rotate the vector in this direction by an angle theta. Okay. Let's say that we rotate it to this direction by an angle theta, like that. All right. Or we could rotate the coordinate system in the opposite direction. Right? If you're rotating the coordinate system, in order to get the same effect, you have to rotate it in the opposite direction. All right. So that's the same thing happening here. This looks like rotating the vector and keeping the coordinate system unchanged. That would be having a coordinate system like this and rotating the vector by an angle like that. All right. Now this corresponds to changing the coordinate system in the opposite direction. All right. Again, we could start with the coordinate system like that and there would be a vector. We could get the same effect here. We could get the same effect by rotating the coordinate system like that by the same angle in the opposite direction. All right. So that's one pictorial way of looking at it. We may say that the cosine of the angle, all right? So by cosine of the angle, it's just a way of calling this inner products, all right? So these components, okay? So this is actually the inner product of a vector and a base vector, all right? This is what we call in classical mechanics as the cosine. We already called these kinds of inner products as the cosine of the angle, all right? So we may say that the cosine of the angle between the state ket and the base ket is the same whether we rotate the state ket counterclockwise or the base ket clockwise. Right? So both these pictures are equivalent. That's what we have seen here. Right? In this case, we are evolving the state ket according to a particular equation. Right? In this case, we are keeping the state ket fixed and we are evolving the base bra according to this equation. All right, both gives the same result. Now, even though we discussed the case of discrete eigenkets, discrete Bayes-Kets, these considerations apply equally well to Bayes-Kets that exhibit a continuous spectrum also, right? So these arguments work equally well for continuous spectrum also. Specifically, if you look at the wave function which is given by bra x vector prime ket alpha, right? You can think of this as either the inner product of the stationary position eigenbra with the moving state ket, like this ket alpha comma t0, sorry, alpha comma t0 equal to 0 at time t, bra x vector prime. We could look at it like this, or you could look at it like this. You can write as bra x prime comma t and then alpha comma t0, simply ket alpha, right? Both these are equivalent. Okay, so you can look at this as the inner product of the stationary position eigenbra with the moving state ket. That would be this case, right? The state ket is moving and the position eigenbra is the same. Okay, but you could also think of it like this. You could think that this eigenbra is actually changing with time and the state ket remains the same, right? In both cases we get the same wave function, right? In both cases we get the same wave function, all right? Now, to illustrate the equivalence between the two pictures further, let's look at transition amplitudes. All right. So this is the situation. Suppose there's a physical system prepared at t equal to 0 to be in an eigenstate of observable A with eigenvalue A prime. So we are saying that initially the system is prepared to be in the state given by ket A prime, right? And at some later time t, we can ask what is the probability amplitude known as the transition amplitude for the system to be found in an eigenstate of observable B with eigenvalue B prime. Okay, so the idea is this: you have the initial state, right? You allow the initial state to evolve with time. Okay, that would be in the Schrodinger picture, right? So we allow this to evolve with time according to Schrodinger picture. Okay, so we get a new state after some time, and then suppose we are making a measurement of B on this state, right? So when we make a measurement of B on this state, we know that it will reduce to one of the eigenkets of operator B. That's the measurement postulate. Okay, so if I make a measurement of B, this state is going to reduce to one of the eigenkets of operator B. All right, now we can ask what is the amplitude, what's the probability amplitude that this change will take place. Right, for that we just take this state, right, and find the component along this direction. In other words, we just look at bra B prime u ket A prime. So this is some state and this is the base bra. Okay, this is what we do in the Schrodinger picture. All right, this A and B can be the same or different. All right, quite generally it could be same or different. Okay, so this is how we find the transition amplitude in the Schrodinger picture. We let the state evolve according to this relation, all right, and then you ask now what's the component of this state along this direction. Right, we know that if we find the component, the modulus square of this will give probability, all right, or this component itself is called as probability amplitude, right? So that will give you the probability amplitude that the system u acting on ket A prime changes to a state ket B prime. Okay, we have discussed these things many times. Okay, that's what we have here, right? So in Schrodinger picture, the state ket evolves according to this, and base bra remains the same. Right? These are the eigenbras of operator B. Right? Now this component will give us the transition amplitude. This will give us what we call as the transition amplitude. All right. Now what happens in the Heisenberg picture? In the Heisenberg picture, state ket does not change. So ket A prime will remain as ket A prime. All right. But the base kets evolve oppositely. We know that in the Heisenberg picture, bra B prime goes to bra B prime in the Heisenberg picture multiplied by u. So the transition amplitude in the Heisenberg picture would be given by bra B prime u ket A prime. And we see that the transition amplitude in the Schrodinger picture is also given by bra B prime u ket A prime. So the transition amplitudes are the same as calculated in both pictures. Right? Now these have to be true. The transition amplitudes, etc., have to be the same in both pictures because these are things that we can actually measure. Alright, so the transition amplitude, the modulus square of the transition amplitude will give us the transition probability, and these transition probabilities can be measured. Right? So in case of measurable results, okay, both pictures better give the same result. Right? And indeed, we see that they both give the same results. Now, since both these are same, we can simply write this transition amplitude as bra b prime u ket a prime. Right? So without making a reference to whether we are talking about the Heisenberg picture or the Schrodinger picture, we can write the transition amplitude in this form. Right? So what we get in this transition amplitude, talking in the Schrodinger picture, this means that you let the state ket a prime evolve into a state u acting on ket a prime. Right? Now this u acting on ket a prime is the state of the system at some time t. Right? If ket a prime is the state at the time t equal to 0, right? Then u t comma 0 acting on ket a prime is the state at some later time, right? This is in the Schrodinger picture. Now we are asking, what happens if I measure operator b in this state, right? What's the probability that I'll get an eigenvalue b prime if I measure observable b on this state, right? And quantum mechanics is quite clear as to how to calculate these probabilities or probability amplitudes. Okay, you just take the state and then project it onto a particular eigenket of observable b. All right. Now this would give you the probability amplitude for measuring an eigenvalue b prime of operator b. Okay, or in other words, this gives the probability amplitude that this system changes into ket b prime on a measurement. Okay. So sometimes this is somewhat inaccurately called as the transition amplitude for going from state ket a prime to state ket b prime. So we just need to be a little bit careful here. When we say that, when we talk about the transition amplitude for going from state ket a prime to state ket b prime, we don't mean the amplitude that ket a prime will evolve into ket b prime. No, this is not what we are talking about. All right. So the thing is that we allow ket a prime to evolve in time, and then we make a measurement, right? So after an evolution and a measurement, what's the probability that you get the state ket b prime? That's the actual question, all right? But somewhat loosely, we always call this as the transition amplitude for going from ket a prime to ket b prime, okay? So let's conclude this section by summarizing the differences between the Schrodinger picture and the Heisenberg picture. Right, so we have a table here, the Schrodinger picture versus the Heisenberg picture. In the Schrodinger picture, the state ket changes with time, observable is stationary, base ket is also stationary. Whereas in the Heisenberg picture, state ket is stationary, observable is moving or changing with time, and the base kets are moving oppositely compared to the state kets in the Schrodinger picture. So we simply say it as moving oppositely. All right. So with that, we'll conclude our discussion of base kets and transition amplitudes. Okay, thank you.